We're now going to talk about using power series to find solutions to differential equations. For this first differential equation that we're going to solve, it'll be a very familiar one which you can easily solve using other methods we've learned. But we'll see how even for such a simple differential equation, here we have a second order linear homogeneous constant coefficient differential equation, and a simple one at that. Even for this, we'll see that there are some nice new insights that we can gain by using power series solutions. The way the idea works for you to use power series as a solution is we start by saying we're going to find a solution y as a function of x. We'll use x as our variable here. We've been using t a lot earlier in class. Y as a function of x is just given by a power series, the sum from n equals 0 to infinity of a sub n x to the n. This is just a naught plus a1x plus a2x squared, etc. Now, if this is our function y, which we wish to be a solution, we can easily compute what y prime is. Y prime of x, and we've seen this before now. This is just a sum from n equals 0 to infinity. We differentiate term by term. We get n a sub n x to the n minus 1. Remember that the n equals 0 term is 0, and so we can ignore the n equals 0 term and think of this as starting from n equals 1, and then we can shift the index, and we can write this as the sum from n equals 0 to infinity, n plus 1 times a sub n plus 1 x to the n. And however you write it, you'll see that that's just a1 plus 2a2x plus 3a3x squared, etc. That's the term-by-term derivative of the function y. And we do the same thing just as we've seen before. Y double prime of x is going to be a sum. Using the first one, we can write it as the sum, differentiating again, n times n minus 1 times a sub n x to the n minus 2. Again, the first two terms, the n equals 0 term and the n equals 1 term, will be 0, so we could start this as n equals 2, and then we can shift the index to write this as a sum from n equals 0 to infinity of n plus 2 times n plus 1, a sub n plus 2 x to the n. And that will look like 2a2 plus 2 times 3 a3x. The next term here would be 4x cubed, so we'd have 3 times 4x squared, and it would keep going like that. Now, the equation y double prime minus y is 0 is the same as y double prime equals y. I just wrote this down earlier. Here's y double prime, what we wrote before. Here's y. If these have to be the same, they have to match for every power of x. Here we have x to the n, and the reason we did this shifting of indexes so that here we have x to the n. That means we need the coefficients to be the same so that a sub n, the coefficient on x to the n for y, has to be the same as n plus 2 times n plus 1 times a sub n plus 2, which is the coefficient on x to the n in y double prime. We need that to be true for every n equals 0, 1, 2, 3, etc. If that's true for every n, then these two functions are identical, and the differential equation will be solved. Yay. Now, what does this tell us if we write a sub n has to be n plus 2 times n plus 1 times a sub n plus 2? Well, we can say for n equals 0, that's a sub 0 has to be 2 times 1 times a sub 2. When n equals 1, I'm going to write that over here. A sub 1 will have to be 3 times 2 times a sub 3. What about a sub 2? A sub 2 has to be 4 times 3 times a sub 4. A sub 3 has to be 5 times 4 times a sub 5. And we could keep going like this, on and on and on. One thing you should notice is the following. Once you know a sub 0, this first equation tells you what a2 is. And knowing A2, that tells you what A4 is. And the next one, knowing what A4 is, it tells you what A6 is, etc. Once you know A1, this equation tells you what A3 is. Once you know A3, this tells you what A5 is, etc. So really everything depends on what A0 and A1 are. And those are arbitrary. We can pick them to be anything we want and then carry out this procedure to find the other coefficients. So we can choose A0 and A1 to be any real numbers. And then let me just rewrite these equations a little bit. I'll solve this for A2. Once you've chosen A0 and A1, A2 has to be A0 over, I'll write it as 1 times 2. A sub 4 is A sub 2 divided by 4 times 3. But A sub 2 is A0 over 1 times 2. So that's the same as A0 over 1 times 2 times 4 times 3, or I'll write it as times 3 times 4. The next one would be A sub 4 is 6 times 5 times A sub 6, which we'll write as A sub 6 equals A sub 4 divided by 5 times 6, which is this whole thing divided by 5 times 6. In other words, A0 over 1 times 2 times 3 times 4 times 5 times 6. So here we have each of the even indexed coefficients just as A0 divided by some number, and it's pretty easy to see what this number is. This is A0 over 2 factorial, this is A0 over 4 factorial, this is A0 over 6 factorial, and this pattern clearly continues. And in the same vein, once you know A1, which we've chosen whatever we want, then A3 is just A1 over 2 times 3. A5 will be A3 over 5 times 4, which is this over 5 times 4, which is the same as A1 over 2 times 3 times 4 times 5, etc. In other words, A3 is A1 over 3 factorial. Even without the 1, that's still 3 factorial. A5 is A1 over 5 factorial, etc. In other words, what we've seen here is that A0 and A1 are things we choose, arbitrary real numbers, and then A2n is just A0 over 2n factorial, and A sub 2n plus 1 is equal to A1 over 2n plus 1 factorial. And this would be for n equals 0, 1, 2, 3, etc. This tells you all of the even indexed coefficients. This tells you all the odd indexed coefficients. Now, what does that let us do to understand what our function is? Well, our function y, this is our solution to y double prime minus y equals 0. This solution y, which is written as the sum of a sub nx to the n in power series form, can be written as a sum over the even index terms. And let me just write that out. The full sum here is a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus etc. I'll write that as the even index terms, a0 plus a2x squared plus a4x to the fourth, etc., plus the odd index terms. And I'm doing this for exactly the reason that there are different formulas for the even and the odd index terms. We have a1x plus a3x cubed plus a5x to the fifth. Those are the odd index terms. And now we'll just put in these formulas that we have above. This is a0 plus a0 over 2 factorial x squared plus a0 over 4 factorial x to the fourth, etc. And here we have a1x plus a3 is a1 over 3 factorial x cubed plus a1 x to the fifth over 5 factorial, etc. And then I'll just factor out the a0 from the terms on this first function. That's a0 times 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial, etc., plus a1 times x plus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. Well, let's put this together. When we're looking for a solution to y double prime minus y equals 0, remember we chose a naught and a1 as arbitrary real numbers. Then our solution y of x was a naught times this function plus a1 times this function. I'm going to call this first function here y sub 1 of x and the second function y sub 2 of x. There are a couple issues now. Have we got the complete general solution to this differential equation? Well, if these functions y1 of x and y2 of x are independent, then we have the set of all linear combinations of two independent functions, which we know will give us our complete general solution to the second order linear homogeneous differential equation that we started with. And I claim they are independent because if you compute the Wronskian of y1 and y2 at 0, you get just exactly the determinant of y1 of 0, y1 prime of 0, I'm sorry, y2 of 0, this looks good, y2 prime, that should be y1 prime, that's not too clear, 0. But notice that for the functions that I have here, this is my y1 of x. y1 is a function where y1 of 0 is exactly 1, and y1 prime of 0 is 0. Just in your head, you can do this real quickly. When you differentiate, that 1 goes away, and you'll start with 2x, and then you'll have a 4x cubed, etc. At 0, that will be 0. For y2, and now things get in the way, but I'll be tricky here. y2 of x is this function. y2 of 0 is easily seen to be 0. And y2 prime of 0, if you just differentiate this in your head and plug in 0, you get 1. In other words, this is exactly the determinant of 1, 0, 0, 1, which is 1. So the Wronskian at 0 is 1, which means the two are independent functions, and we thus have a complete general solution. Now let's ask, is this satisfying? Well, all of you could look at that differential equation and probably solve in your heads and get the complete general solution right away. From what we learned over the last few weeks, the characteristic equation is just r squared minus 1 equals 0. The solutions to this are r equals plus or minus 1, which means that y equals e to the x, and I'll call it y1 equals e to the x. I don't want to call it y1 because we're using y1 separately. So let me give it a, mathematicians like to do this. I'll call it y1 twiddle equals e to the x, and y2 twiddle equals e to the minus x. These are both solutions, which you can check in your head real quickly. These are honest-to-goodness solutions of our differential equation. They're easily seen to be independent, and the general solution to the differential equation is the set of all linear combinations of these two functions. But if you look at our functions, y1 and y2, they're different. They're not e to the x and e to the minus x. They're functions given with these different power series. Does that mean that we haven't done things correctly? Well, not necessarily. I claim, in fact, that we have done everything correctly, and we have the correct general solution to our differential equation. Here's a question, though. What do our functions y1 and y2 look like? Well, remember here that e to the x has power series representation, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. And notice that this is valid for all x. I haven't talked about radius of convergence, but one thing you'll see is that both our function y1 and y2, and certainly the e to the x here given by this series, these series all converge for all x, all real numbers x. They have radius of convergence, which is infinite, and everything will work over the entire real line here. What is e to the minus x? Well, it's just what you get when you plug in minus x for x here. So that's 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial, etc. And now notice something interesting. If you add these two together, the odd powers will all cancel, and you'll be doubling up on the even powers. So if you add the two together, e to the x plus e to the minus x over 2, you'll get exactly 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. This is what we were calling y1 of x. Of course, there's a name for this. This is written as cosh. I didn't even write it correctly. Let me get rid of that. X, the hyperbolic cosine of x. It's e to the x plus e to the minus x over 2. And of course, you can all probably see where we're going. The hyperbolic sine of x, which is e to the x minus e to the minus x all over 2. If you take this, you take e to the x, subtract e to the minus x, all the even powers of x cancel, and the odd powers of x just double. So when you divide by 2, you get the odd terms in e to the x expansion. You get x plus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And this is what we called y2 of x. So now when you see that these functions, y1 and y2, that we came up with, which were our two individual, in fact, independent solutions to the differential equation, which we came up with by using power series, were the hyperbolic cosine and the hyperbolic sine functions. Those are already two different linear combinations of e to the x and e to the minus x, so they're certainly valid solutions. Our set of all linear combinations of hyperbolic cosine and hyperbolic sine is exactly the same as the set of all linear combinations of e to the x and e to the minus x. But as I said, there's actually something nicer about using hyperbolic cosine and hyperbolic sine here as a fundamental set of solutions, because they have these properties here. And finally, let's just finish that off here. Why is that nice in some way? Well, what if I want to solve y double prime minus y equals 0 with an initial condition, say y of 0 equals 7 and y prime of 0 equals negative 19? Well, because, and here unfortunately it's way up here, because for my solutions y1 and y2, the hyperbolic cosine and hyperbolic sine functions, we have y1 of 0 is 1, y1 prime of 0 is 0, and y2 of 0 is 0, and y2 prime of 0 is 1, I can write my solution right away without having to solve any complicated system of equations. When I say complicated system, it would be a system of two linear equations and two unknowns. That's not very complicated once you've finished 10th grade, certainly, maybe earlier. But anyway, we can just write y of x equals 7 times what I'll call y1 of x, what we called earlier y1 of x, that's the hyperbolic cosine function, minus 19 y2 of x. We know that any linear combination of y1 and y2 will be a solution, so y is a solution to our differential equation. We know that when you plug in 0, y2 of 0 is 0, y1 of 0 is 1, so y of 0 will be exactly 7, and when you differentiate, you can see that when you plug in 0, you'll get exactly this number, minus 19. So in some ways, this is the nice, or most nice, fundamental set of solutions, hyperbolic cosine and hyperbolic sine, though any fundamental set of solutions is perfectly good, and you can just solve for the coefficients you need if you want to solve an initial value problem.